a vector quantity which is more similar to scalar quantities, what we already did in our maybe BSc classes or before that also. So now we'll go further in the direction. So here we'll see. So if you have earlier last class we see that how vector quantity, let's say you have a vector and if it is changing or it is a function of any variable, then how you can differentiate that. So now if you have instead of vector, if you have, let's say you have a scalar field. Field means so some quantity is distributed in a space, or maybe in 2 dimension, 3 dimension, 1 dimension, let's say in general in space. For example, let's say you have heat distributed in a space, and how that heat is distributed, like so if you have let's say a candle uh, is placed at some point, let's say O, in this figure. If you follow the figure in the first page of this last document, how that heat is changing. Like if you are close to the candle, you feel more hot, and if you go away from the this source, then you will feel bit colder and colder. So the heat will decrease. So means the temperature will decrease, not the heat. So the temperature will decrease. So how this temperature is changing in that uh, space, then so that if you want to know that how your um, uh, temperature is changing, and the direct, and also uh, so let's say if you are uh, at point O, and let's say if you want to find the change of temperature at point, let's say P, which is so let's say point T, which is, so at point T your temperature is a function of both X, Y, and Z, means how the point is there, like whether the point is on the surface or point is on the space somewhere. So depending on the coordinates, so the temperature of that point may be different. So now if you go from that T to some other point, how the temperature will change, that if you want to calculate, so how you can do that in so okay, let's say so your temperature, so okay, so so now let's say if you have so the change rate of change in the temperature along X, Y, and Z. So as it is a function of X, Y, Z, all these three variables. So now so the rate of change along the rate of change in the temperature along X and Y and Z, you can calculate by taking the partial derivative. Let's say del T del X, del T del Y, and del T del Z. That means how that is changing uh, in the space. So now if you so this is along each direction, but overall how the so if you want to understand how this is changing, uh, if you add all the three components, so this is three components, so now you have to do it in a vectorically, like t del x I cap. So I is the uh, along the unit vector along x-axis, and similarly along y-axis and z-axis. So if you do a vector addition of these three components, then you can find the total rate of change in your function t. So this is in general. So I can write I cap del del x, I cap del x plus j cap del y and k cap del z. It act as an operator on your function t and give you the rate of change of that function t. Um, so now, where t is an scalar quantity. So this operator is called the del operator, and we write as a capital delta, and delta t is called, or sometimes called grad t, gradient of t, or grad t is the gradient of the function t, or scalar function t. So now, in general, so this is for the, let's say, temperature distribution. For if you have any function, let's say any scalar function, let's say phi, then we can write grad phi, which is more in general we use this um, term like grad phi. We are more used to this quantity like grad phi, where phi is the scalar function or scalar field, you can say. So grad phi is equal to um, I cap del phi del x plus j cap del phi del y plus k cap del phi del z. So this is in general like temperature only. So now our aim is, so this is the total rate of change in the function or scalar function phi. So now if you want to find the change in phi, so this is the rate of change. So if you want to find the actual change in phi due to if you displace by uh, some amount, let's say dx, dy, and dz. So all these three infinitesimal displacement. So how the your phi is going to change. So how I can find that. So to find that, so you know from your earlier class that if you have, so del phi del x is the rate of change along your x-axis. So if you multiply by dx, so that will give you the total change along your um, of your function phi along x-axis. So del phi del x dx is the total change along the x-axis. Similarly, del phi del y multiplied by dy is the total change along y. Similarly, z also, del phi del z dz. So this will give you the total change in your function phi, that is d phi. That means d phi is equal to, I can write del phi del x in page 4. Actually we are in page 4, the top of the page 4. So d phi is equal to del phi del x into dx plus del phi del y into dy plus del phi del z into dz. So this is your total change in your function phi. So now this d phi also I can write more compactly is equal to grad phi dot dr. So this multiplication del phi del x into dx, del phi plus del phi del y into dy plus del phi del z into dz. So this product can be written as grad phi dot dr. So dr is nothing but your this dr your all the small component or your displacement in case of our xyz coordinate system. So I can write dr is equal to I cap dx plus j cap dy plus k cap dz. So these are, as I said, dx, dy, dz are the small change along x, y, and z direction. So this is the I can write in the vector form dr is equal to I cap dx plus j cap dy plus k cap dz. So this is, so now d phi is equal to grad phi dot dr. So that means grad phi dot dr will give you the change in your function, um, small or infinitesimal change in your function phi, which is d phi. So now, if you have, so this is for in general, and phi is could be any potential or any scalar field. So now, if you have a equipotential surface or the um, um, the scalar field is having, so there is a so it is uniformly distributed a scalar field, and also this the distribution forms a equipotential surface. That means your phi xyz, which is a function of xyz, is a constant, and that means at, so so it will form a surface, and on the surface the value of the function at each point on the surface will be the same. That's why this constant c. So this is, you know, that phi xyz is equal to c will give you a surface with equipotent, means so the everywhere on the surface the value of the function is fixed. So that is the equipotential surface. So the potential, if it is potential function, potential, or some other function also, you can name in the same like this. So it could be temperature also sometime. So it depends which function or which quantity you are representing. So now, uh, so for this kind of situation where you have equipotential surface, what happened to the gradient of that surface? So let's see. So let's say you have two. Uh, so in the figure, page 4. So let's say I have a point on the surface. Uh, so I have a point P on the surface, and then I have drawn another surface which d phi plus delta phi. Let's say another surface having so this P is the surface, phi is equal to C, and Q is the surface. Let's say phi plus delta phi, some another surface, equipotential surface. So now, uh, so R and R plus delta R are the position vector of P and Q. So there are 2 points. One is on the surface phi, another point Q is on the surface phi plus delta phi. So now the position vector of P and Q are R and R plus delta R. So in that you can write PQ is equal to actually the delta R. So now delta R is very small, and get phi dot dr, already we know that get phi dot dr is equal to your d phi. So now if the point Q and P are on the same surface and very close by, so let's say I bring the Q point close to the, very close to the point P on the same surface. And see, if you look into this figure, so if you find that delta are actually approaching towards the tangent of the surface phi at point P, and if P and Q are the same surface, on the same surface, then delta phi is equal to 0 because they are on the same surface. So phi will not change on the equipotential surface. That's why the definition of equipotential surface. That means that phi dot dr is equal to 0. So now as I said, so if you approach Q to P, so it will be along the tangent, and grad phi dot dr is equal to 0 indicates that grad phi and dr both are perpendicular to each other, and dr is the tangent. So that means grad phi is the normal to the surface at P, right? That means this grad phi represent the, so grad phi point to the normal to the surface phi for this equipotential surface phi to the phi at point P, right? That means grad phi is nothing but the normal to the surface. And now we can write, let's say I have represented normal by unit vector, let's say n cap, capital N cap. So come to the page 5, to the next page, and so grad phi is a vector. I can write mod grad phi times n cap. N cap is nothing but the unit vector along the normal to the surface, and delta n. So let's say uh, you have displaced your surface from P to another surface. So you are going along the normal. So and then the normal distance. That means now you are changing your surface from P to some, let's say, some another. You are creating another surface by displacing that surface along the normal, and that normal distance you are moving is the delta n. So then the change in phi in the direction of the normal. So if you are moving along the normal, so then how much is the change in the function phi? So the phi is through the point P. So now d phi dn, actually the change in your function along the normal. So if you are changing along the normal, dn, and your change in the function is d phi. So d phi dn is the rate of change of phi along the normal. So this I can write, as you can see from d phi dn, I can write in a limit form like del phi del n, limit delta n tends to 0. So this is the differentiation formula, and this delta phi I can write grad phi dot dr from the earlier. Now grad phi I can write modulus of grad phi times n cap. So this is the actually the grad phi vector, and dot dr. So dot dr, this quantity now n cap dot dr. So if you look into that figure, so you'll find that n cap dot dr is nothing but dr cos theta. So if you project your dr vector along the normal, and that is nothing but your normal distance delta n. That means n cap dot dr is delta n. So now in this limit you can convert to d phi dn is equal to modulus of grad phi. That means your change of your function phi along the normal is nothing but the um, the modulus of your grad phi. So this is actually the things like so if you have uh, so it's like if you have a function, let's say function any function f, which is a uh, function of y, so or x, let's say, so f of x. So now if you change x, so how much is your changing in your function. So this is df dx. So the rate of change in your function. So df dx. So df dx, because grad phi is a vector quantity. So if you take the modulus, that means the amount of rate of change, not the direction. So amount of change on rate of change is grad phi. So which is equivalent to d phi dn, which is nothing but if you are changing along the normal, the rate of change of your function phi along the normal. So now, so this is the similar things like other derivative means other derivative things also. Only thing is that your variable is your normal, like d phi dn. So rather than grad phi, you have x y z component, but in n you are thinking that okay, normal itself is your variable, so you can write in the both way. So if you know the normal, you can calculate directly d phi uh, d phi dn. So this is equivalent to your gradient of phi, right? So this is the thing. Either you know how the phi is changing in xyz, you can calculate grad phi uh, taking all the component, or if you know the normal, you can differentiate this function with respect to the normal also. Okay, so now if you have let's say you have the grad phi. So now if you want to check the grad phi or the rate of change of your function phi, or let's say any scalar field phi along a particular direction. So not always you want it, maybe you need in some other direction, because always so you know that so in the vector, if you know a vector, so sometimes we want to know the component of that vector, like in other direction how much component it is having, or what is the influence of that vector in some other direction. So for that, what you can do is that so grad phi is your gradient uh, of your scalar field phi. Now if you take a projection of that along any other uh, vector or any other direction, let's say here it is I have written it is d, or it could be any direction vector. So you want uh, the component of your grad phi along other uh, direction. So what you have to do, you just have to project that on that other direction or other uh, vector. For example, here it is d. So the grad phi dot d is the component of grad phi along the vector d. So this is called the directional derivative. That means you want the derivative in a particular direction. So this is the actual meaning of directional derivative. So you know that, for example, for known problem, let's say you have a force is acting along, let's say some, uh, so acting along a direction which is having a angle theta to the x-axis. So if you want to know the influence or the component of your force along x-axis, so how you do that, you just take a projection of your vector f on the x-axis, so you will get the influence of your force along x-axis. So that is, you can say the directional direction of f along your x-axis is the same thing here, your directional derivative of your function phi or scalar field phi along some particular direction. So uh, this is the thing. So now if you have, let's say if you have r, which is the in the figure, you see that your r is actually the, or rather you can say along PQ, right? So now if you have uh, so now if you want to get the change of your phi along r, that means del phi del r is nothing but, so you can use the same limit formula, like limit delta tends to 0 del phi del r, which is uh, similar the derivative things. So now uh, so so let's say in your along delta r, your unit vector is, let's say, n prime. So that is p to q. In that direction, let's say your uh, unit vector is n prime cap. So now uh, from uh, from the last page, in page 5, so you can see that del delta n divided by delta r is equal to cos theta. So if you see the figure also on page 4, then also you see that del r del n divided by del r is nothing but the cos theta. So now I can write delta r is equal to delta n by cos theta, and cos theta is nothing but n cap dot n prime cap. That means delta r is nothing but delta is equal to delta n divided by n prime n cap dot n prime cap. So now del phi del r I can write, if you substitute this uh, value of delta r here, then you will find that limit delta r tends to 0, delta n delta phi uh, del n delta n divided by n cap dot n prime cap, which is I can rearrange and write n cap dot n prime cap into del phi del n. And del phi del n is nothing but your modulus of your grad phi. So and n cap grad phi is nothing but your vector grad phi, and grad phi, so this becomes grad phi dot n prime cap. So del phi del r is nothing but grad phi dot n prime cap. So you see that along n prime, the component of del phi del sorry grad phi, the component of grad phi along n prime, that is from p to q, is del phi del r. So it's similar things what I uh, said for the uh, directional derivative. So if you want to find the directional derivative of a scalar field, so you have to take that you have to find the grad phi, and then you have to find the direction, and then just take the dot product. So you will get the directional derivative of that scalar function along that direction. For example, so in page 6, so there is an example. So so everybody is there on page 6, or anyone can respond?
Yes, sir.
Yes, sir.
Okay, yeah, okay, thank you. So in so there is an example. So so for the directional derivative, so these things are important when you uh, let's say want to calculate some differentiation, and then you want to take some projection of that along some other direction. So this could be important in those kind of situation. So let's say in I have a surface which is represented by x square, y square, z square, and I want to uh, calculate the directional derivative of this function or this sort uh, any, let's say it is any scalar function along at point 1 1 minus 1 at this point, and along the tangent of the curve x is equal to e exponential t, and y is equal to sine 2t plus 1, and z is equal to 1 minus cos t, where at t is equal to 0. So this is another curve x is equal to e to the power t, and y is equal to sine 2t plus 2t, and z is equal to 1 minus cos t. So at t is equal to 0, I have to calculate the tangent to this curve, and then along that tangent, I have to calculate the directional derivative of my function phi, which is x square y square z square at point 1 1 minus 1. So how we can do that? So first I have to calculate the uh, gradient of phi, which is I've calculated, which is nothing but, or if you take all this del phi, del x, del phi, del y, and del phi, del z, and I cap, j cap, k cap in this direction, so you can calculate that grad phi. So now grad phi at point 1 1 minus 1. So I just put the value of x, y, z, and then I can get grad phi at point 1 1 minus 1 is equal to 2y cap plus 2j cap minus 2k cap. So this is my grad phi. So now I have to find the directional derivative of this grad phi along the tangent to the curve which is given in terms of this variable. So x, y, z, which is also there is a condition at t is equal to 0. So now so for that curve, the position vector x is equal to sorry, r is equal to x cap I cap plus sorry, x I cap plus y j cap plus z k cap. So this is my position vector for that curve, corresponding to that curve. So now I can just put all these x, y, z values which are given in the questions itself. So now for the tangent, I can take the derivative of this position vector with respect to the variable which is given t. So the tangent, if it will come as I plus 2 j cap. So now along that tangent, I have to take the directional derivative. So my aim is to just calculate the dot product between grad phi and tangent. So if you do that, grad phi dot t, then you will find that 2 I cap plus 2 j cap plus, okay, okay, it's not plus, it's minus 2 k cap and dot hmm. Okay, so if you do that, you will get 6 by root over of 5. Okay, actually some people said, okay, I have not shared my screen yet. So maybe some people join late. So for those who join late, for them, I'm saying that this interactive things will come from next week, because once I arrange that setup. For the time being, please for this next two class, you just go through this PDF and then follow the PDF. And I think these classes are not so for repetition for you. Maybe most of the people or most of the students have gone through this class, right, in your BSc, and yeah, mainly BSc. So this is for just for refreshing, so that you can practice some problems, and so that is main idea. So for this, because I will give you some assignments, and so those you have to solve. So it is just for refreshment of your previous stuff, whatever you have learned in your BSc, because we'll go slowly, and new things will come. But for this vector things, I think it is everybody has gone through this classes. Only things I will do is that some give you some assignments, so that you practice those your previous um, things, because this will be useful for competitive exams, uh, because these are in the syllabus for most of the national uh, exams, competitive exams. Okay, so I'll not go further, and what I will like to